Black holes. Just the name conjures up images of cosmic monsters, devouring everything in their path. These objects are some of the most fascinating and mysterious entities in the universe. They represent the limits of our understanding of physics, where gravity reigns supreme. What happens inside these cosmic abysses? Where do they lead? The answers, if we can ever find them, may hold the key to unlocking some of the deepest secrets of the cosmos. For centuries, black holes were merely theoretical constructs, predicted by Einstein's theory of general relativity. Now, thanks to advances in astronomy, we have direct evidence of their existence. We've observed the orbits of stars around supermassive black holes at the centers of galaxies, and we've even captured images of their shadows. But what exactly are black holes? They are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine a place where the fabric of space itself is being pulled inwards faster than the speed of light. That's a black hole. The boundary of a black hole is called the event horizon. Once something crosses the event horizon, it's gone forever, at least from our perspective. What happens inside is a mystery. Imagine approaching a black hole in a spaceship. From a distance, it might not look like much, just a dark spot against the backdrop of stars. But as you get closer, you'd start to feel its gravitational pull. Time would slow down for you relative to someone observing from a safe distance. Your spaceship's clock would tick slower, and your transmissions back to Earth would become increasingly redshifted, their wavelength stretched out by the intense gravity. As you approach the event horizon, the point of no return, things would get really strange. The black hole's gravity would start to distort the fabric of space-time around you. You might see strange optical effects, like multiple images of the same object, as light rays are bent around the black hole. If you were to shine a flashlight back towards the universe you were leaving behind, you would see the beam of light bend inwards towards the black hole. The closer you get to the event horizon, the more the light bends, until, at the event horizon itself, even light traveling directly outwards is pulled back in. This is why black holes appear black. No light can escape from them. Once you cross the event horizon, there's no turning back. You're now caught in the black hole's inescapable gravitational grip. What happens next is a subject of much speculation, but physicists believe that you would experience a phenomenon known as spaghettification. Here's how it works. Imagine your feet are closer to the black hole than your head. Because gravity is stronger the closer you are to a massive object, your feet would experience a much stronger gravitational pull than your head. This difference in gravitational force would stretch your body out, like spaghetti dough being pulled and stretched. As you fall deeper into the black hole, the difference in gravitational force between your head and your feet would become more and more extreme. You'd be stretched thinner and thinner until eventually the atoms themselves would be torn apart. At the very center of a black hole, according to general relativity, lies a point of infinite density and zero volume known as a singularity. Here, all our known laws of physics break down. It's a place where space and time as we know them cease to exist. Think of the singularity as the point at the very bottom of a bottomless pit. It's a point of infinite curvature in space-time, where the gravitational field becomes infinitely strong. What happens at the singularity is anyone's guess. Some theories suggest that it might be a gateway to another universe, or perhaps even a different point in time within our own universe. However, it's important to note that our current understanding of physics is likely incomplete when it comes to singularities. Quantum mechanics, the theory that governs the behavior of matter at the subatomic level, suggests that the singularity might not be a point of infinite density after all. Instead, it might be something else entirely, something we don't yet have the theoretical tools to describe. Section 5. White holes, cosmic fountains. While black holes are defined by their incredible inward pull, white holes represent a theoretical opposite. Imagine a region of spacetime where nothing can enter, but matter and energy are constantly spewing out. This is the essence of a white hole, a hypothetical region of spacetime that acts like the reverse of a black hole. Just as nothing can escape a black hole once it crosses the event horizon, nothing can enter a white hole's event horizon from the outside. While black holes are thought to be formed from the collapse of massive stars, the formation of a white hole remains a mystery. Some theories suggest that white holes could be the other end of black holes, connected by hypothetical tunnels through space-time called wormholes. Section 6. Wormholes, shortcuts through space and time. Wormholes, also known as Einstein-Rosen bridges, are theoretical shortcuts through spacetime. Imagine folding a piece of paper in half and poking a hole through it. That hole is a shortcut between 2 points on the paper that would otherwise be far apart. That's the basic idea behind a wormhole. While Einstein's theory of general relativity allows for the possibility of wormholes, they remain highly speculative. Creating a wormhole would require exotic matter with negative mass-energy density, something that has never been observed. Furthermore, even if wormholes do exist, their stability is questionable. They might collapse too quickly for anything to travel through them. Despite these challenges, wormholes continue to capture the imagination of scientists and science fiction writers alike. The possibility of traveling vast distances across the universe, or even to other universes, is a tantalizing one. Section 7. Hawking radiation, black holes aren't so black. In the 1970s, Stephen Hawking, one of the most brilliant minds of our time, made a groundbreaking discovery that shook our understanding of black holes. He proposed that black holes aren't entirely black after all. Instead, they emit a faint radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Hawking radiation arises from the creation of virtual particle pairs near the event horizon. According to quantum mechanics, empty space is not truly empty, but is teeming with virtual particles that constantly pop into and out of existence. Normally, these virtual particle pairs annihilate each other almost immediately. However, at the event horizon, one particle might fall into the black hole while the other escapes, carrying away a tiny bit of the black hole's mass energy. Section 8. The information paradox, lost in the abyss. Hawking radiation leads to a profound puzzle known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed. Yet, if a black hole evaporates completely through Hawking radiation, what happens to all the information that fell into it? This paradox has puzzled physicists for decades. Some argue that information is lost, which would violate quantum mechanics. Others believe that information is somehow encoded in the Hawking radiation itself. But how this happens is still a mystery. The information paradox highlights the conflict between general relativity and quantum mechanics, two of the most successful theories in physics. Resolving this paradox may require a new theory of quantum gravity, a theory that unifies these two pillars of modern physics. Section 9. The multiverse connection, portals to other realities. Some physicists have speculated that black holes could be portals to other universes. This idea stems from the concept of the multiverse, which proposes that our universe is just one of many universes that exist. According to this theory, each universe within the multiverse could have different physical laws and constants. Black holes, with their extreme gravitational conditions, might be able to punch through the fabric of spacetime, connecting our universe to others. While the idea of black holes as gateways to other universes is highly speculative, it's a fascinating possibility. Section 10. Current and future research. Unraveling the mysteries. Despite decades of research, black holes remain some of the most enigmatic objects in the universe. However, scientists are making progress in unraveling their mysteries. The Event Horizon Telescope, a global network of radio telescopes, recently captured the first ever image of a black hole's shadow, providing further confirmation of general relativity's predictions. Gravitational wave detectors like LIGO and Virgo have detected the ripples in spacetime caused by the collisions of black holes, giving us a new way to study these objects. Future observations and theoretical breakthroughs will undoubtedly shed more light on these cosmic enigmas. Section 11. Conclusion: the never-ending quest to understand black holes. Black holes, once considered mere mathematical curiosities, have emerged as some of the most intriguing objects in the cosmos. They are regions where gravity reigns supreme, where space and time are warped beyond recognition, and where our current laws of physics may break down. The study of black holes is a journey into the unknown, a quest to understand the most extreme environments in the universe. While we have learned much about these enigmatic objects, many mysteries remain. Where do black holes lead? What happens at the singularity? Do white holes and wormholes exist? These are just a few of the questions that continue to drive scientific inquiry. As we delve deeper into the mysteries of black holes, we are likely to uncover new and unexpected wonders. The universe is full of surprises, And the study of black holes reminds us of the vastness of our ignorance and the boundless potential of scientific discovery.